Okay folks, thank you all for coming. My name is Eric Woldridge. I'm a professor here at Somerset Community College for Additive Manufacturing in our pre-engineering program. What we're doing here today is demonstrating some of the research and findings we've done with one of our studies. And I appreciate you all coming from your different industries and giving us the time of day, so to speak, to hear what we have to say. We did get some really interesting information. And at the end, we'll have some time for questions and taking a look at the lab and see what we've got going on here in terms of our prototyping and production using additive manufacturing. So to begin, let's start off with why we're here. Quick background, my actual degree is a mechanical engineer and architectural engineer. That's what I got my licenses are in, and also I'm a registered architect. So production of things, buildings or small components, is really my passion. I love to teach about it too, and I love to actually share the knowledge, especially with the new technology that comes along that is this disruptive. I want to make sure that folks understand that. Now, which leads actually sort of into our problem. Our underlying problem with additive manufacturing right now in our particular region is the lack of integration. Right now we are seeing article after article, news publication, all sorts of things about the technology, but the problem that we're seeing, especially in the regions that we kind of operate in, are a lack of interest or consideration. Basically, we feel that there is an additive manufacturing AM disruptive wave that's starting to happen, and we're worried that our regions, our manufacturers, and those folks that are actually typically contract manufacturers, they're producing parts and products for larger enterprise level companies, they're not aware of what's coming. They're not aware of the metal additive manufacturing projects that are underway. They're not aware of the shift over that's starting to occur with the enterprise level companies such as GE and Caterpillar and even several aerospace companies like Boeing and Airbus. They're just not aware, and they don't necessarily see it as something they should be paying attention to. With that, we want to make sure that that's not the case. We don't want them to be left behind, so what we were proposing is, well, perhaps maybe you don't want to go into metal right now, but you should at least be aware of the technology. You should at least be aware of its potential within what you do currently. Your current business model can have additive manufacturing integration at low cost. So we want them to be prepared, but we understand they're not going to be investing large amounts of money in large metal printing systems. They might be able to afford some low-cost options. So we need to give them a carrot. We need to basically put something out there for these companies to see and realize there is money to be made or there is money to be saved with their current operations. And that money is representative of low-cost additive manufacturing. By saving large amounts of money with a low-cost machine, it can get the additive integration into the door, into the company, get them used to the process, get them seeing the potential, learning how to optimize, and then as that larger disruptive wave comes along or new contracts open up that can only be done with additive, these companies will be ready to take that step. We don't want them to be left behind. We know they can't get in right now. We want them to be thinking about getting in as soon as possible. So our primary objective is to demonstrate that FDM, or the typical fusion deposition modeling, or FFF, which is also referred to as fused filament fabrication, essentially low-cost FDM machines can be used to generate significant savings and provide a serious convenience within companies that already have an existing operation. Maybe it's in their machine tool side, maybe it's in their maintenance department, maybe it's within marketing, who knows. But we want to show that low-cost equipment, desktop 3D printers, can be added to your current company and be used more than just prototyping. They can be used to actually make things to make your business better. Make your machines work better, optimize your current process with a very, very low risk factor. You can get in the door very easy, low entry, get started making things, produce savings, justify the cost of the equipment, and then go on beyond that. So whatever's our carrot, that's our objective, and our basic research looked at what low-cost FDM is. So this is the type of equipment we're talking about. We're talking about systems that are fairly straightforward. You know, equipment that you can see right there, that's a Luzbot Taz. We have a Prusa right there, an Ultimaker in those cases. You know, low-cost equipment, and we're probably talking less than $3,000, $2,500, in some cases $800, that can be bought, installed in a company, and start producing parts with hardly any entry barrier whatsoever. So, the real question was, who do we start with? What companies do we engage and say, okay, here's the opportunity, this is a machine you want to try out, where do we go? So do we start off with aerospace? You know, we actually have aerospace contractors in our region making parts for the aerospace industry. We have automotive. We have a very strong automotive manufacturing industry in our region. And so maybe that should be the group we should help to integrate. We should connect with their maintenance departments and show them, hey, there's applications that you can do right now that you've been missing out on. There's optimizations waiting to happen. Or maybe we should look at heavy equipment. Companies like Caterpillar, they're not too far from our service region. And they have large industrial equipment industries. They make a lot of big, heavy parts. So if we do some FDM with them, they can see that there's applications for the metal side very easily. So all these are possibilities. You know, we're trying to think which one do we want to go with. And so obviously, the obvious choice was baking cookies. So we decided that baking cookies was the way to go. We should use FDM in the manufacturing of baked goods. So we partnered up with Hearthside Foods, and why not? Because, you know, obviously everybody, according to the webpage, everybody that works there is highly attractive. So we want to get in on, you know, that kind of industry right off the bat. You know, this is where we want to work, and we want to help them make cookies better. We want to help do something with specifically their maintenance department and their controls operators to actually make their process better using low-cost 3D printing equipment. Maybe a machine that's $2,500 or less, maybe one's even $800 or less, and demonstrate that there is money to be made or saved. So we partner up with Hearthside. Now, actually, background on Hearthside, it's actually an international company. One of the locations is about 30 minutes from our main campus here in Somerset, and they essentially produce baked goods. It's a manufacturing. They actually, on their website, they kind of call it the Great American Manufacturing Renaissance. So we wanted to part with them, help them do that process, but with the intent of, if successful, or even if we learn something about the process, we can turn around and integrate there with additive manufacturing, and then they can help to integrate their entire system. And they're very interested in doing this. You know, with the competitive nature of their market, so many locations, additive, if it has a serious impact, can be used to do a great number of changes all across the world, and they want to get started here at the ground floor right in our region. So we were definitely interested in making this happen for them because of the fact that it can go nationwide and internationally. So with that in mind, we started small parts. Most of the parts typically around, you know, a few inches. One was about 11, 12, something like that. Narrow brackets, those kind of things. We start off with small parts that they have that are existing parts for them, and they either manufacture themselves using their own fabrication department, or they actually just purchase these. Now these are typical brackets, little connectors, things that that no one really thinks about, but either wear out, get broken, and have to be replaced. So we were curious on, first of all, you know, how much money is represented in the purchasing or the internal conventional fabrication of such products, and then of course, how much can we actually make them with using low-cost FDM machines. So here's a couple of examples of the parts that you see here. We have a couple brackets that were two-parters. There's the long one that you see, very, very small ones here or there, all that kind of thing. Nothing really special. You even notice the geometry itself is actually very, very simple. So keeping that in mind, we're good to go with the design. Let's see. Go. And so we set off to doing the process. Now typically all of the designs that you saw here are actually just good old-fashioned CAD models. They were actually done with a very simple, easy-to-use CAD package, and they were actually provided to us by Hearthside. So they provided the models, a little CAD work there, and we did the printing. So we actually used a couple different machines for most of these, and what you see in the model on the upper left there is the one of the brackets, the Donner or Dorner bracket, I believe they refer to it as. And you'll notice we batch printed that. We didn't actually just print one at a time, we did a total of 6. And then we have a couple other brackets down there at the bottom, and there's an example of one of the machines that we use. This is the Prusa i3 Mark II unit. And that particular unit is of great interest to us because it only costs about $800 shipped to your location. Now that comes in kit form, but you can actually pay a couple $100 and they'll assemble it and still ship it. So about $800 to $1,000 either get you a kit version of it or fully assembled, ready to go. We like this printer. I mean, this system works well. It has good detail, good controls. Just super pleased with this unit. So we actually printed quite a few of the parts on this particular printer. One of the best products or best features about this whole process is that number right there in the middle that you see, the 24/7. These printers can run 24 hours, 7 days a week, if you want them to. And we'll talk a little bit more about that later on. But we started off by printing those parts, and turns out pretty straightforward. Really didn't have a lot of problem. We knew the settings, we knew what to do, and those parts were pretty easy to fabricate. So as you can see, these are actually some of the parts in actual use at Hearthside. One of them is just sitting there holding a clicker on it, or a camera bracket. I don't know, I think it's a sensor or something of that nature. You see those kind of things. Now there's just a cap plate that you see right there, and I think that actually has another little sensor on it. I'm not real sure. We didn't really know what the parts did. All we knew is they said, we need these parts, make them for us. And it's not a big deal. We load the files up, we do a little slicing, and we actually let the printers take over from there. And these parts are pretty basic. Now these parts aren't optimized for additive manufacturing. That's a whole other topic of conversation. But they're pretty easy to produce. So, comes down to it, the bottom line of these small parts. What was actually done? Now we've got the graphic there of the ins and outs of how much it usually costs them. But here's what you're interested in. These numbers at the bottom. Conventional costs. It used to cost them $815.48 to get the quantity and the type of these parts they needed for this batch. You know, we actually did this project, it was roughly around 60 days or so of different files being sent and sent back and those sort of things. So, you know, these were just trial runs. But it normally cost them roughly $815 to actually get these parts made or purchased when they ordered. Then, we did the FDM. Here's what you need to know. That same number of parts that normally cost them $815 cost us about $27. So to produce the parts that they were paying $815 for cost us about $27 just to print them. Now keep in mind the concept here is not that you're hiring a new person to do this technology. The concept is you have an existing person in the company, we'll talk about this a little bit more, but you just buy a printer and you start printing the parts that you need. That's why we're not factoring in shipping costs to ship them from one site to the next, because it's assumed that one day the printer will be in their location. So we didn't worry about that issue. By the way, that $815 that you see didn't include some of the shipping costs, so it's actually likely higher. But anyway, bottom dollar, $788, $789 of savings represented in just that first few batches of parts. Literally, in the first few runs of testing this out, they saved enough money to pay for the machine. They could have bought the machine we printed the majority of those parts on with the savings. Just over a few months of just trying it out, just seeing what they could do. They could have already bought the machine and paid for itself. So that's a big deal. And so we consider it a success. We're like, well, this works. This is an optimization consideration because not only can they now make their own parts, but they can also maybe optimize, come up with new designs, and just keep rolling like gangbusters in their creations. So we decided, let's go bigger. Let's do something bigger and better. Let's do something that folks would really appreciate. Let's do something that just gets attention, and therefore we came up with the funnel project. Here's one of the prototypes right here. So this is still Hearthside, of course, and you can kind of see some of the stuff at your tables and stations there of different parts and different pieces that we worked with. But this is the funnel that they needed replaced. And let me explain what this funnel does. You see, you don't want to actually have, your cookies and products are actually made by machines, right? They're baked and they go through all kinds of different processes. You don't want to have any like metal shillings when you bite into your Oreo cookies, right? So to avoid this problem, over on there on the bottom right, you see that we have, or my right on the screen, I guess you can say. So you see there they have this little diagram, and this is essentially what happens. You see the funnel. The funnel actually is in the middle of a metal detector. So to make sure that you're not getting any metal shillings into your cookies when you're eating them, they have a metal detector to just basically sense that, and it will shut down the system if it detects any metal. But obviously in that case, you're probably not going to be making your actual funnel that has to funnel this down out of sheet metal in that case, right? So they have these nylon large funnels of this size. So the chute drops the baked goods down the funnel, the detector is surrounding it, it sees if it detects anything, and then they drop them into the bag out of the funnel. Pretty simple, pretty straightforward, and obviously have to have one of these funnels facilitate this. Now they have about 16 of these machines, so keep that in mind. The cost of one of these funnels to be manufactured conventionally, the way that they've always bought these things, is about $800 plus shipping. So they're spending about $800 on shipping these funnels to their plus shipping to these funnels to their factory to actually produce this. They have 16 machines, and they told me, they said essentially, you know, about every time we place an order for these things, they go up another $75. So it's not even like static. And to be fair, I can understand why, because it's not like they're molding these funnels. They're actually fabricating these funnels in pieces and doing some, you know, basically some polymer welding to put the pieces together. You can see the seams. So keep that in mind. Somebody's having to put a lot of time and effort and material into making this thing, and obviously they're getting paid for it, $800. And there's nothing really special about the design. You know, it's just a funnel. So they currently only order about 6 of these units a year due to budget constraints. They're incredibly expensive, and you know, when something breaks, you've got to take it out of somebody's budget. And they have an issue with that because one of these machines goes down because of this. They may not just be ready to throw another $800 away at a new part. So what they typically do is they get about 6 a year, 6 new ones, and they just keep doing repairs. So if one breaks, one wears out, something like that happens, they just go in and they have their maintenance guys do some fabrication work and put it back into service. Not, you know, do their best work if they can repair it, and obviously it's going to fail again soon. And that's a manual expense they have to spend, but it's still cheaper than them spending another $800 to get it done. Now, that limitation of 6 is because they can't afford more, you know, they just don't want to budget for that much. But they said that if they could have 24, they could actually improve their overall process. Now that's kind of out there. That's just way too much expense that they're going to throw at their maintenance budget. So it's not really even an option for them. But if they did have 24 a year, they could actually streamline the process. You know, one goes down, they don't have to hold it down for long to do repair work. They just pop the next one on, or they have a regular maintenance schedule that just keeps them replaced. So if they had 24, roughly, they could actually keep all their machines working in their best possible situation and minimize their downtime. But let's face it, 24 of these at $800 a pop, that's just a little bit too much. So the question was, could a low-cost FDM system be used to make this happen for them? Could a 3D printer that you can buy off any roughly a regular website and get set up, could it produce what they needed? So we set out trying the options. So, you know, our target here is on the upper right there. You see the funnel that we're shooting for, and the answer is yes. Yes, we can. Now we tried a couple different printers for this process. This one actually is one of the printed versions, and it was done on one of our raw stock Deltas. You can see it in the back of my truck there. That's a great company up in northern Indiana, Michigan line, that actually makes these things. They're great guys to work with. Learned a lot from them. So we tried on the Delta, and it can make it, but it didn't make it as well as we'd like it to. We wanted a little something extra. So we looked at one of the other units that's actually on the market and has a really good extruder system, and that is the one in the center there. That's the Luzbot TAZ 6 specifically. Now we chose it specifically because of the fact that its build volume is right at the threshold of this particular funnel. And this is going to put us in, you know, ideal situation for what we want. And price tag, $2,500. So you can't be a price tag like that, and that's actually including shipping. So it shows up, and we get started with the process to kind of see, because we know we can't just use any material for this. We need to use a specific material that is actually FDA approved. And the material that they're using right now is nylon, so we should probably start there. So we do some tests. We do some trial runs. You can see some of the setups that we've done, some of the parts there, small little funnels, medium-sized funnels, you know, funnels all over the place. But we simply just order some nylon off a typical website. Nylon 618 was our first run. We got an order of about a half a kilogram of that and ran it, got the settings dialed in. And then we switched over to doing nylon 680. It's actually FDA approved material, and then printed that. And the answer, yes. Yes, we can. So there's our Hearthside representative, Mr. Charlie there, who's about to take the first version of it back for testing, and pretty happy with the process. You know, essentially we just printed something that had to be manually made previously, and it's going to solve their problem using a unit we can buy off the internet for $2,500, and one that can actually run 24/7. Now, keeping in mind, we didn't get there just right off the bat. We had to go through a lot of trial and error. Now, one of the great things about these printers is that 24/7 operational profile, because to fabricate one of these, that TAS has to run for around 40 to 50 hours, depending on settings. That's a long time. Great thing is, you don't have to watch it. You can just turn it on and walk away. A few little settings, we'll talk about that later on, and what you can do to make that happen. That's a serious factor in the oversight of this whole concept, is these machines can just run and run and run with little to no supervision. So different sizes, different things that happen to us. First of all, when we started off, we were getting on that, what you see on the bottom left there, is a funny curvature. So we did have a problem with the original CAD model of the funnel. Again, this came from Hearthside, that their software didn't produce a nice smooth round. We thought it was the slicing settings on the printer side, but it actually wasn't. It was actually the model. So all we had to do to fix that was actually just go in and fix the computer model, the CAD model, and then reslice it, and it was fine. So that took care of that problem. And of course, getting the settings dialed in to produce the parts in the right size and the nylon temperature settings, which actually was a lot easier than we thought it was going to be, was pretty straightforward. We did have a little funny effect, and we associate this with nylon and its its response to moisture. So we get these little funny bubbles on the inside of the funnel, not on the outside, and we think we can take care of that through settings. Now, we had already planned on the funnel being to have a little post-finishing work, a little smoothing out anyway, and these things just prick right off, so it's not like a big deal, but it's something we're going to work on to figure that out. But little bubbles was an issue. But down toward the bottom middle there, you see those little red lines. That was a crucial issue. So this was one of the first ones that we did, and we had this layer delamination effect, where essentially one layer was not adhering to other layers. Now, it wasn't every single layer, it was almost in intervals, but they weren't actually regular intervals. So we actually did the settings on this one at 0.2, which means it's about 0.2 millimeters of layer height. And we were getting these just weird delaminations. So turned around, changed the settings to go down half, or actually 0.05 of a millimeter. So we took the layer height down from 2 or 0.2 to 0.15. Change the temperature just a little bit, change the speed just a little bit, and let it roll, and then we got a much better result. Basically, better layer adhesion. Layer to layer adhesion was a pretty significant deal there. So we made those changes, and suddenly we took care of the problem, which is great. We love it when that happens. Quick fixes are awesome, but we learned a lot from that process. Now on the right, you see the little foot pads there. We call them hold pads. They're like a little model we have. We just add to files to help hold the actual first layer down a little bit, because most thermoplastics have a tendency to shrink as they cool down and has a tendency to curl the outside perimeters up. We add these little hold pads onto the design, no matter what the design is, to hold it down in place. Use a little adhesive on the bed, and we actually have a funnel that sits. Now, cylindrical objects actually typically don't have a whole lot of problem, mainly because their curling is in this cylindrical form, so we don't have that pulling effect we do with rectangular objects. But we had the hold pads on, because if you're going to print for 40 to 50 hours, what's the problem there? And actually, the great thing about these little things is they're so small and so thin, you can just snip them off with scissors, and they actually don't impact the model at all. They just get built into the overall design. So that's why we use them a lot, just to hold things down to make sure we're not going to lose the print over the course of the time. But those are the kind of things that we had to work out in the process, which leads us to the whole concept of this settings thing. It's all in the settings. So what you see is the software that we use to actually do the slicing. It's called Simplify 3D. It's sort of a universal software where it controls 3D printers of all different types and features. And it works really well, and it gives us a ton of options and controls. I think there's like over 100 different setting choices we can make with this software. And it gives us just the ultimate control in the performance of the machine, and typically can take a decent machine and turn it into a great machine just because of the slicing. But you can see all the little tabs and windows here, the stacked. Those are all different setting tabs that we can make adjustments to get our features right. And the top view is actually the placement of the model. The bottom view there that you see in the green is actually the simulation mode, where it shows us how it's going to print this object, shows us the layers, shows us any errors that might be happening in the model we don't realize, all kinds of things. We love that simulation mode. It also gives us the prediction of time and material consumed. So, to get to the bottom lines, here's what you need to know. Here's what you're probably most interested in. To actually purchase the equipment, $2,500. Shipped right to your site. It's great. The nylon, FDA approved nylon 680, roughly costs around something like 30 to $40 for a half a kilogram, based on who you're buying it from, but not a big deal. What you're most concerned with, though, is right here. Keep in mind this thing used to be actually conventionally manufactured for $800. We estimate that even if you consider a little bit of maintenance and wear of the equipment and the actual energy consumed, you're topping out at maybe $48 per funnel. $48 per funnel. Less than $50 to make a $800 part. And it's made with the majority of time spent overnight, off-shift work by a machine that costs $2,500. So also as an extra bonus, we did some checks on our model versus dimensional accuracy on the actual part. We had basically a plus or minus tolerance of 0.22 millimeters, or 87 thousandths of an inch. Pretty good for a $2,500 machine that sits on your desktop. Could be at your house, really. Pretty pleased with that. So as mentioned, about 40 to 50 hours worth of fab time, 24/7 operation, which essentially means that this piece of equipment could literally pay for itself in less than a week. Now think about that. When was the last time you got to buy a piece of CNC equipment that actually paid for itself in less than a week? And by the way, these things are CNC-based controls. In fact, it's G-code that's running the whole system. So it's not like it's a new coding technology. It's something we've had for decades. But, 1 week payoff time. We already saw in the small parts that we paid for it in a couple months, and that's just because, we send some files, print some files, send them back. We weren't in a big rush. Unfortunately, for this particular project, we were kind of a big rush because it took a while to get the printer in. We only had a few weeks to actually get the project done. So, we were in a rush to get it right, and it fell together within a matter of like 4 weeks or less in terms of starting work on the printer and actually having the funnels ready to go. So keep that in mind. Investment of only $2,500 pays for itself in less than a week. What's not to like? And then you can use it, after you make your 24, which would have cost you over $19,000. You can make 24 of these units for about $1,200. And now, not only does that save you money, it also allows you to optimize your existing process. And we don't have any data yet to show it, but, obviously, we're going to reduce the number of failed product batch losses because we don't have the funnel problem we used to have to. All we're going to have to do is find a good maintenance schedule to replace these when the machine's up or down, and now we don't have any lost batches due to the funnel breaking or having an error in the bag filling process. So we're going to save money. We're going to optimize the whole process and save even more money because we've given an option to actually save money. And, this thing might be running 2 months to produce 24. Then you can use it to produce whatever you want to after that. All those other parts. Of course, most companies we anticipate, once they get into this process, might have one printer for one job just sitting there making parts all the time. Another printer for another job, there for random projects. Who knows? The key thing is, with numbers like these, where's the risk? What's not worth trying to see what you can do to integrate and optimize your process. So it's hard to argue with numbers like that, which was really exciting for us because, we were looking for some for some silver bullets. We were looking for some examples to say, hey, here are some clear numbers. Here's the biggest carrot you need. Money waiting to be saved with a little bit of additive manufacturing integration. Now, considerations associated with what we did and kind of how this works. One of the key things you have to understand is you can't really do this unless you have someone with some CAD skills. The fact of the matter is, someone has to do computer modeling, especially if you want to look at optimization. One of the things with Hearthside, this funnel is actually a generic funnel. It has 16 machines, but actually, they don't really need this shape for all 16 machines. The shape could be changed, and they've even pointed that out, but they just go with the shape that's sort of universal. But there's even optimizations that could be going with a funnel that's not as wide, not as tall, sloped differently to slow the goods down, or to maybe speed them up, whatever the case may be. So there needs to be someone within the operation that has some CAD skills, but not necessarily advanced CAD skills. We foresee a person looking at some training, maybe 30 hours of training could probably take care of all they need for both the CAD and the slicing applications. Even less, obviously, if they already have some CAD skills. But keep in mind, we're talking about manufacturers, so most manufacturers have some connection to folks internally that have some CAD skills or CAD capabilities. So we don't see that as a real entry problem. Now, AEM, the FDM, additive manufacturing training, obviously that training is going to have to be there for this to work and can be packaged up fairly easily. But, really, in all honesty, we're probably talking about a week of training or less to get the machine going. So, and then get the hang of actually production. Obviously, the little nuances and those kind of things that we learn on the fly, learn on the job, but really, you could actually train someone. We actually have some programs and some certificates that could actually get that training pretty fast, too. Now, one thing we do point out is in this equipment, we always recommend a backup power supply. Power goes out and the machine goes down, it's hour 42 out of 50, that's a pretty depressing moment. So, typical backup power supply, even ones that are using computers, can work for these machines because these things don't actually pull that much wattage. Most of their power supplies are like 600 watts or less. So you can actually get a backup system to work just fine. And on the same line is we typically like to program our codes onto SD cards and just plug them into the machines instead of like trying to run them from a computer. That way you don't have failures due to communication errors. One of the big things, though, that has to be present for this to really take effect is that optimizing mentality, optimization. A person that realizes, hey, I could do something better, or maybe we could fix this so it doesn't break anymore. Maybe we could redesign that. We've done project after project where we've taken apart, people come to us and say, this part breaks, can you recreate it? And we'll say, yes, we can recreate it, but while we're at it, why don't you just have us make it better so it doesn't fail again? And that's the mentality we want to go for. We want to go for people to get the foot in the door with the equipment, get it going, solve some problems, but then turn around and do something better and more. Now, overall goal, AEM integration with this particular company and international impact. We want this message to be shared with all of Hearthside's sister operations. We want to get this out there to them, and then we want to turn around and get it out to everyone else. There is money to be saved or made using low-cost FDM. Now that does bring, of course, the question of intellectual property. Again, the models that we received came straight from Hearthside. We trust that there's not like a copyright infringement or anything like that. And to be honest, I don't see how there would be. These parts are just too simple and too generic in form for copyright situation to actually apply. Also, with that in mind, keep in mind that our copyright laws are typically geared toward, sales of reproduced items, not making something for yourself internally. So there's a little bit of gray area to begin with that I think is going to be a real issue with additive because it makes things so easy to create something out there. I do foresee that companies are going to have to start considering that even in their replacement parts, because if they're going to produce a big piece of equipment and they make a lot of money off of aftermarket sales for replacement parts, and suddenly that part is being printed by somebody internally and they no longer need it. And it's not been a real big issue because people will fab stuff for themselves all the time and within companies to replace their own parts. But sometimes that's inconvenient. It takes up time, takes up labor, and it's usually cheaper for them to just go buy it than have someone make it internally. Now that's not the case. When the machine can turn around and actually make it for you, then we're talking about a whole different deal where they're not going to be buying so much stuff out there. So that's a consideration too. So a lot of the experience of this, it's pretty fast-paced, but we see a huge amount of potential associated with this work. So a lot of options for different examples and opportunities for folks to take advantage of. Come on, it just kind of easy around that way. He's right over there. Sorry. So with this in mind, we see a lot of applications for folks to get in on early, get in on now, because additive is coming, and it's coming in production parts. And we know most companies aren't ready to start switching over to do production parts with additive yet, but there's going to be contracts that are going to happen. So this is the way they get your feet wet. You step in, you try a little bit. I mean, again, for a manufacturer, this is not a risk. I mean, there's no, the entry level, the barrier here is nothing compared to some of the equipment costs that some of these manufacturers normally purchase. So this is just a step to try to get in, save some money, see the possibilities, and then go from there. We have a lot of opportunity with this, and so many companies are just not aware of how much money is there to be saved, but also what's coming down the pipeline. So do appreciate your time today and all the attentiveness. That hopefully you find this useful to your particular field. You find this helpful to what you all do, and you can actually find ways to integrate this as best as possible. So at this point in time, I'll just take a little break for a second, and we'll field some questions. Yes, sir. So how long to get this kind of up and running? So essentially, like I said, we actually had the equipment show up a little bit late, much later than we wanted to, especially on the TAS situation. The small parts, we were able to jump right in on that. But actually, we had the equipment up and running that day when it arrived, and started the testing on the next day. So turnaround time and getting equipment up and running, not usually a big deal. Optimization and getting the settings just right, probably when you add in all the time together, maybe about a week to get all those settings right. The problem is you got to account for the time spent in printing, so that usually extends it on out. But actual man hours, not that bad. Anyone else? Go ahead. Yes, I'm glad you asked that question. Anyone can use this technology. There is no limit, and I really defy someone to find a professional field that can actually use this technology in some way to optimize what they are doing. Everything from arts and crafts to medical science, even culinary applications, they're all there. So even if you just look at their own maintenance process, what do they use to keep their equipment running, is all possible. So anyone can use the technology, and the training level itself is kind of varied. Most companies, if they have someone with CAD, that makes it pretty easy to integrate this. If they don't have any CAD experience, CAD is going to be a must as part of it, but not always. So in some cases, like let's say you're a household situation, you can actually download a lot of these files and not have any CAD experience and start printing things. We're actually seeing several companies spending time and resources to develop printers that are all about this cloud database where you can just download and print instead of actually having to do any model yourself. And they're hitting those markets where folks aren't going to have any CAD skills but still want to make parts or still want to get in on this fabrication and action. So really, it's not hard to get into this industry, and anyone can use it. Any others? That's a good question. Okay, so long-term printing. As I mentioned, one of the major problems with long-term printing is making sure your power doesn't go out. One of our off-site locations where we've got one of our large units, we might be running that for 2 or 3 days. I think right now, around 50 to 60 hours is our record, is the only thing, the longest print we've done. But, if the power goes out, typically don't want to actually try to rerun from where it never comes back on or if a glitch happens. The other major, what actually happens more, or used to, is the communication glitch. So when we first got the slicing software, there was sort of this universal one, we loved using it. So we load a part in, hit the slicing settings, and say, go print. And it starts printing. But it's across a USB cable, which is hooked to a computer on the internet, which sometimes updates itself for random reasons. And we would just lose files over and over until we start switching away from, Wi-Fi connectivity and landline connectivity and switch it to just using secure digital cards and just SD cards, put the code on it, plug it in, walk away. Don't have to have a computer hooked to the printer, nothing's dedicated, and that took care of a lot of our problems. So once you get those factors taken care of and keep the environment, you know, as long as there's no real odd environmental factors like gusts of wind and those kind of things, you're pretty good to go. So give it power, give it a backup if you need to, and give it an SD card. Other questions? Any others? Okay. Durability of parts. That's an excellent question. So what happens is, in terms of durability, there's a lot of different science associated with additive production of parts than conventional. Conventional is always, you know, conventional is typically solid material through and through, you know, cut from a block or injection molded. So those properties are pretty static, right? So with additives, since there's so much internal control, it could be open spaces, could be different designs, could be shell counts, infills, you know, it's a whole different science unto itself. But as far as material goes, the material is the same material. You know, we can print the same stuff that's being used to make Lego blocks. It's the same nylon. It's just produced in a different form for us to use. So the material is still the same. It's what you have to really think about what your product or design is going to be used for, where the stresses are going to be, and what it needs to do. Then you select your material and print it with that material. Now typically we focus mostly on polymers, but there's all types of different resins that have unique properties. Obviously the metal printing has unique properties. So the durability is not really a question, a limited question. Durability is, it can be as durable as you want it to be. You can use whatever, you use material you want to use, you can use the settings you want to use to make it. So it can be super strong, super durable, or not. We design, if we know a part's not going to receive a lot of stress, if it's going to be like a very, very low impact part that's going to be like hanging a banner from a ceiling, we're not going to design it to be super strong. We're going to design it to be super hollow and super lightweight. And even the design's not the big deal. The design's the same, it's just the settings control that. So it's kind of as durable as you want it to be. Others? Okay, good question. Everywhere is the answer. So where do I see this going? Everywhere. Again, I really don't think there's not a professional field that can't integrate this in some form or fashion. There's every imaginable application of profession can use this technology. Everything from marketing and business to just, you know, general maintenance, even home maintenance, you know, toys and gifts. You know, we're about to produce some stuff for Mother's Day here shortly. So it's just unlimited, and it's only going to get better. And the reason we say it's only going to get better is because the technology has jumped drastically since this consumer desktop printer came to being and some of the patents protecting them expired. You know, it's just huge differences, leaps and bounds over a short period of time, and they just get better and faster. And it's crazy when you look back at some of these printers. Go back to this one. Let's see if we got one right here. There in the bottom right, see all that orange? That's all printed parts. So literally this particular printer has like a majority of its structural components printed by its siblings. I mean, it's printers printing parts for printers. And so when you have the ability to do that, that means any company can get into a whole new market. They don't have to go through, you know, so much machine time and expense to get parts made for whatever their product is. They can start making a product and use printers to make the production line to get them started. You know, it just reduces so many barriers that makes the technology totally unlimited. Now what you're going to see is the enterprise level integration of additive to produce parts that you could not make any other way. And here's why. If I can actually design a part with not having to concern myself whatsoever with can somebody make it, because I assume the additive can, and for the most part it can. If I don't have to worry about that, I can design for the exact perfect solution to my problem. I don't have to live, I can actually live in the theoretical in some ways. I can make a fluid line do weird and crazy curves to hit where I need to get. I can do different shapes to create different types of velocities, different types of circulations within hydraulic systems. I can redesign everything to solve the problem perfectly, not close as I can get it within conventional manufacturing means. So what you're going to see, and many companies are already starting to demonstrate they're doing this. They're switching to parts that solve the problem the best, and then they turn around and say, additive, go make it. So that's why I said there's going to be contracts coming out that additive is the only option. They're not going to send out a design that says, hey, we need 100,000 of these, you know, can you conventionally make it? Because the answer is going to be no. They're going to say, we need 100,000 of these per this ASTM standard, and we need them done, you know, within the next 2 or 3 months. And they're only going to be for the people that actually can do additive. Now, granted, I just made up those numbers totally, but keep in mind that you're going to see a shift in contract manufacturing for additive because the designs are so exotic. But the designs are going to be so exotic because that solves the problem that they want to solve. It doesn't get them close, it solves the problem or makes it better. You know, Caterpillar gave us some crazy impressive data when they switched over to using additive on one of their engine systems, and it's going to increase its operational lifespan ridiculously low, by a ridiculous factor. It was crazy. So you're going to see more and more of that, and it's going to cost some jobs, but it's going to create some serious opportunities for those who get on board early. Anything else? Going back, you mentioned the material thing. We'll throw this out there. So different types of materials. We've got everything from PLA, basically a cornstarch type of organic-based plastic that's very eco-friendly. We've got nylons, we've got ABS, we've got HIPs, we've got thermopolyurethane. Basically, you know, whatever material is out there typically is either going to be printable or is already printable now, because the printers represent this whole new platform for materials. All kinds of material research, all kinds of companies are getting into the material production for these printers because it's almost like apps on a smartphone. You know, we got a smartphone, suddenly this app industry popped up. Now we've got this printer platform, this whole materials industry is going to pop up, and we're just seeing the big players, small players getting into that. So about whatever material, fourth dimension, you know, where it actually changes over time, has 3 dimensions, and then the 4th dimension is time, you're going to see more and more of that. The research is just, you know, inundated with new types of material applications. So you're just going to see it over and over. Anything else? What type of projects? So we work on a lot. We've done everything from replacement parts for biology departments to biomedical models for training, prototypes. We're just seeing so many different applications. Right now we're also working on with other companies to integrate AM into what they do, and we're going to get a lot more into the materials research. What we like to do is start to hit the metal printing and also the more exotic polymer printing. So we're bringing in some new equipment. They can reach higher temperatures, control better, and do a lot of materials research. We definitely want to hit some of the biomedical because that's a custom field already, and we want to look at casts and prosthesis and those kind of things. So a lot going on, a lot of research that we're going to get to take advantage of, a lot of equipment out there we're going to be able to employ and do some great stuff. So we're pretty excited about what's on the horizon. Anything else? Okay, all right. I appreciate your time today. We'll take a look at some of the equipment, and contact information is on the screen there. Let us know if you have any questions. Thank you very much.